and this lecture is on the introduction to pre-stressed concrete. The topics included in today's lecture are introduction to pre-stressed concrete, principle of pre-stressing, advantages of pre-stressed concrete, pre-stressing steel, high-strength concrete used for pre-stressed construction, and methods of pre-stressing. Objectives of the lecture are that at the end of this lecture, students will be able to explain principle of pre-stressing and classify methods of pre-stressing. The background of this pre-stressed concrete is related to the reinforced concrete. You know, concrete is basically a compressive material with strength and tension being relatively low. And pre-stressing applies a pre-compression force to the member that reduces or eliminates undesirable tensile stresses that would otherwise be present. Okay, the principle of pre-stressing has been explained in this figure. If you look at this figure, on the left top, you can see a reinforced concrete beam, simply supported beam subjected to 3-point loads. As the load is increased, the tensile stresses will keep on increasing with the increase in load. If reinforcing bars are present on the tension side, then the beam will not collapse. If there are no tensile reinforcing steel, then the beam may collapse. So every beam, when subjected to loads, will undergo some tensile stresses depending on the end conditions. For example, if you look at the other beam on the right top, this is the cantilever beam, and when this cantilever beam is loaded, tensile stresses are produced in the upper part of the beam, and therefore that part must be reinforced with some appropriate reinforcing bars in order to avoid the collapse, premature collapse of the beam. So this was the concept used in reinforced concrete, and we have seen this in many examples on the design of beams and slabs, that reinforcement was needed in the location where tensile stresses were produced by the loads. Okay, so the problem in all these situations was that tensile stresses were produced in the locations, and since concrete is weak in tension, so in order to reinforce, in order to strengthen those weak parts of concrete, reinforcing bars are placed. And once reinforcing bars are placed at those locations, reinforcing bar will be perfectly bonded with concrete. This is a basic assumption in the mechanics of reinforced concrete, that reinforcing steel and concrete are perfectly bonded. So when reinforced steel and concrete are perfectly bonded, so any strands which were produced before introducing reinforcing bars in concrete would be now taken by the combined action of reinforcing steel and concrete, and thereby avoiding cracking and collapsing of reinforced of the concrete beam. So the problem in all the situation was tensile stresses produced. Now, the question is, if we can avoid these tensile stresses to occur, then there will be no need of reinforcing bars to be placed in those locations. So how can we do this? Now, let's look at this, the same concrete beam, reinforced concrete beam. Let's say when the concrete beam, before the concrete beam is loaded, what we do is that we pre-compress the lower part of the beam. Pre-compress means that we press these two ends of the beam, from this end and this end. We press this by some mechanism, and if we are able to press this beam at this location up to an extent where, when the load is kept on the beam and the tensile stresses are produced in the beam, so whatever compression has been produced before the beam is subjected to loading, that will be cancelled, and it is quite possible it can be designed, the beam can be designed in such a manner. In other words, this pre-compression force can be designed in such a manner that whatever load is coming on the beam, and the tensile stresses which are produced by those loads may be equal, can be equal to the pre-compressive force. So the pre-compressive force which was present before the application of the load will be cancelled out, with the result that there will be no tensile stresses produced in the lower part of the beam. Okay, so this is the principle of this stressing. You can look at other situation where the beam is subjected to, where there is a cantilever beam, and it is also subjected to some load, 2-point loads. Tensile stresses are produced in the upper fibers. If we can compress this upper fiber, pre-compress before the application of the load with some mechanism. If we can pre-compress this part, push this end to this end, and compress this upper part of the beam, when this beam is now loaded, the pre-compression will become zero. At most, this is possible to design this pre-compression force in such a manner that whatever tensile stresses are produced due to the load, that will be equal to the pre-compressive force, with the result that no tensile stresses will be produced in the upper part of the beam. So this is possible. The only thing is that we have to use that we have to now learn what mechanism of the application of force is possible in order to produce this pre-compression force. Mathematically, this principle of pre-stressing can be explained with these figures. In the first figure, there is a beam which is subjected to a point load at the midspan, and this is simply supported beam. You know that tensile stresses will be produced in the lower part of the beam, and compressive forces will be produced in the upper part of the beam. So if FC is compressive stress in the upper part, and FT is the tensile stresses in the lower part of the beam, FC and FT will be equal as long as the beam is in the elastic range. Okay. And as you move, you know that for a point load, the bending moment diagram will vary in a triangular manner like this, with the maximum bending moment occurring at the midspan. And you know that the tensile stress can be calculated using the flexure formula F is equal to my by I. F is equal to my by I is famous flexure formula, which is applicable as long as the beam is in the linear elastic range. So the maximum bending moment occurs at the midspan, maximum tensile stresses and maximum compressive stresses will occur at the midspan, because F is a function of M. As you move towards the support, with the decrease in bending moment, F tensile stress and compressive stresses both will keep on decreasing towards the support, and finally at the support these stresses will be zero because M is zero at the support. Similarly, if you look at the variation of flexure stresses through depth, so you have flexure stress at the neutral axis equal to 0, and the flexure stress increases as you move towards the top and bottom of the beam from the neutral axis, with the maximum stresses occurring in the top, maximum compressive stresses occurring in the top fiber of the beam, and maximum tensile stresses occurring on the lower fibers of the beam. Okay. Now let's say we apply a pre-compressive force or pre-compression. You can see this force P and P. We will discuss this, how this force P can be applied, what are the available tools to apply this force P, but let's discuss this at the moment that this is possible to apply a compressive force P as shown in this figure before the application of the load. The load is not yet been applied. So before the application of the load Q, we will pre-compress this beam with force P. Okay, so once we pre-compress this beam with force P at the centroid, you know that P will produce stress which will be equal to P divided by A. You know this because this is an axial force, and the compressive stress produced on the cross section of this beam will be equal to FC is equal to P divided by A. This is you know this very well, and the whole beam will be in a state of compression. So compressive stresses of the same magnitude will produce all along the length of the beam. Because this force is same all along the length of the beam, it applied at the ends of the beam. So force P will produce stress Fc is equal to P divided by AC, and AC is the cross-sectional area of the beam. Correct? Now, when the beam is in the pre-compression state, we apply the load Q. When the load Q is applied, so as discussed earlier, for this load W, the same state of stress will be produced, but then this state of stress which is produced by Q will be added to the already existing state of stress. The already existing state of stress is P divided by F is equal to P divided by it is already there. And at the mid-span, we know that at the mid-span, Fc and Ft will be Maxium. So when Fc and Ft at the mid-span are added to this Fc due to the load Q, and Ft tensile stress also due to the load Q, the Fc and Ft will be equal. You know this as long as the beam is in the linear elastic range. Now, what will be the state of stress at the mid-span? The state of stress at the mid-span will be equal to Fc, which is a pre-compression stress existing before, which exists before application of load Q. So Fc plus Fc will become 2Fc, and Fc plus Ft will be 0, because we have applied force P such that the stresses produced by this Fc will become equal to Ft. So this is a pre-compression force. We have done it like this. Not every force P will be equal to this Ft, but this is if this P is of such a magnitude that it produces Ft equal to Fc, then Ft will be equal to 0. And this is possible. How? You know that Q will produce a force, a stress Ft. You know this in the beginning, so you can calculate this Ft and Fc. Okay, and once you calculate this, Fc is equal to P divided by A. So P is equal to Fc into A. You can calculate P required to produce Fc equal to Ft. So then Fc plus Ft will be equal to 0. And in the top fibers, the compressive stress twice of the previous case. In the previous case, load W was applied without a pre-compressive force. So twice the compressive force will be produced, compressive stress will be produced in the upper part of the beam with 0 tensile stresses. And as you know, that concrete is weak in tension, concrete is very good in compression. So if compressive stresses are doubled, so it is not a matter of concern for us. The matter of concern for us is tensile stress, and tensile stresses have become 0. This will occur at the mid-span. At any other location, what will be the situation? For example, at this location, at the location between mid-span between the load and the support. Between the load and the support at this location, for example, at this location, you know that Fc and Ft will be less than what Fc, Ft were at the mid-span. Let's say that Fc is half of that. So that will be 0.5 Fc, and it will be equal to 0.5 Ft, plus Fc and Ft must be equal as long as the beam is in the linear elastic range. But this will be constant because P is all along at every section stress, the pre-compression force will produce the same state of stress, that is Fc is equal to P divided by A. So this Fc will be added to 0.5 Fc, so this will be 1.5 Fc, and Fc minus 0.5 Ft will be 0.5 Fc. So there will be a state of stress at this location with 1.5 Fc in the upper fibers of the beam and 0.5 Fc in the lower fibers of the beam. There will be no tensile stresses at this location. Similarly, if you take a section at the support, so at the support, Fc and Ft both, they are 0, plus bending moment is 0 here, and you will have a state of stress only due to the pre-compression force. So this state of stress will vary from the support to the mid-span, where the load has been applied, point load has been applied, and this will be the worst situation. At any other location between Q and the support, between the load and the support, there will be no tensile stresses produced in the beam. Rather, there will be compressive stresses produced in the beam and in the lower part of the beam as well as in the upper part of the beam. Only at the mid-span, you will have 0 tensile stresses. Okay. Now, let's say that this force P is not applied at the uh, centroid of the beam. This is applied at an eccentricity equal to h divided by 6. H is the total depth of the beam. H by 2. H by 2 is half of the beam depth, and h by 6 is 1/6 of the beam depth. It is, let's say, applied at eccentricity P below the centroid equal to h by 6. When this force P is applied at this before the load 2Q is applied, so what will be the situation of stress? Load P will produce one stress equal to P divided by A, as was the case in the earlier example in the figure B, illustrated in figure B. So this will be a state of stress produced by this force P equal to Fc is equal to P divided by A. But this force P will also produce bending moment. Bending moment, you can see that this, when this force P is applied here, so P multiplied by this E will produce a bending moment which will bend the beam upward, which will bend the beam slightly upward. Okay, and this bending moment will be equal to P times E, and this bending moment will be constant all along the length of the beam. If you apply this, if you want to draw the bending moment diagram for this, this will be a straight line. The whole section will be in the tension. In the upper part of the beam will be in tension, the lower will be in compression, but the bending moment will be constant all along the length of the beam. Okay, now this, when this P produces the state of stress P by A, and plus tensile stress is equal to minus Ft, tensile stress in the upper fiber, and compressive stresses in the lower fibers. So we have designed this force P such that this produces this Ft1 equal to Fc. So in Fc, you know that Fc is equal to P divided by A. So once this Fc is added to this minus Ft1, which is produced by this eccentric application of the force P, then Fc minus Ft will give us a 0 tensile stress. And everything that we are discussing right now is before the application of the load. Before the load has not yet been applied. So before the application of the load, the force P will produce this state of stress plus this state of stress, and this state of stress which we are talking about, this minus Fc1, this will also remain constant all along the length of the beam, because P times E is a bending moment which is constant all along the length of the beam. So Fc minus Ft1 is equal to 0, and Fc plus Fc is equal to 2Fc. 0 and 2Fc is the state of stress. Tensile stresses are 0 in the upper fibers of the beam, but with the twice of compressive stresses in the lower fibers of the beam. And you know that when load 2Q is applied on the beam, it will produce tensile stress in the lower part of the beam, not in the upper part of the beam. So if you have twice the compressive stresses in the lower part of the beam, you can double the load. You can double the load, and so the double load will produce an Ft, which will at most make this 2Fc equal to 0. And this is what we want. We don't want any tensile stresses, or if there are tensile stresses, they must be within the range. So if this is the state of stress, 0 and 2Fc, 0 in the upper part and 2Fc in the lower part of the beam. Now, let's say we apply the load now, 0 2Fc. Okay, at the midspan now, this load 2Q will produce, let's say, 2Fc, twice the compressive stresses that were produced by Q alone, and 2Ft will be equal to 2Fc. So 2Fc plus 0 will be 2Fc, and 2Fc plus 2Ft will be 0. With the net, with the end result that the capacity of the beam has been doubled if force P is applied at eccentricity, at some eccentricity, in this case equal to h by 6, which means that eccentric application of force P will will double the load. Will double the load, and eccentric application of force P is better than concentric application of the load P. So it has its own disadvantages, which we will discuss in the coming slides. Okay, now let's see what happens if this force P is applied at an eccentricity, but the eccentricity is variable. With the variable eccentricity, the bending moment will not remain constant all along the length of the beam, the bending moment will be in fact the opposite of the bending moment produced by 2q. The bending moment produced by this P will be in this direction, and the bending moment produced by 2q will be in this direction. So if before the application of load, this bending moment is produced in this manner, okay, and after the application of the load 2q is produced, this will completely cancel this with no tensile stresses living in the beam, and the beam will be perfectly in the compression, in compression. So now let's discuss this, what will happen if this eccentricity, the force P is applied at eccentricity. For this, we will have to now investigate the beam at midspan as well as at the end of the beam, at the support of the beam. Okay, what will happen at the midspan? First of all, let's say we are discussing the midspan. So at the midspan, you have seen that when force P is applied, this will produce P by A force, stress, P by A stress will be produced at this location, plus the tensile stress is equal to the compression tensile stresses in the upper part and compressive stresses in the lower part. This will be FC, this is also FC, and this is FT. Okay, and so when this is added, it will give us 0 in the upper part, FT and FC, sorry, tensile stress in the upper part. So this FC plus FT, this will give us 0 stress in the upper part of the beam before the application of the load, and this FC and FC will give us 2FC at the midspan. So before the application of the load, the state of stress at the midspan is 0 and 2FC. Okay. Now, when the load is applied, 2q load is applied, we have 2FC compressive stresses in the upper part of the beam and twice of that tensile stresses in the lower part of the beam. So that when this 2FC is added to this will give us 2FC, and 2FC, this will give us 0. What will happen at the end of the beam? At the end of the beam, unlike the previous case where there was a bending moment produced by P, the bending moment here is 0. The bending moment here is 0. So this will be only this part of the before the compression, before the application of the load. The tensile stresses which were produced by the beam in the upper part all along the length of the beam are not produced now all along the length. The tensile stresses are only produced at the midspan, and the tensile stresses are going to become 0 at the end of the beam. So only this FC part will be present at the end of the beam, here at this location, and at the end of the beam, this will be the situation FC is equal to this FC and FC. So at the midspan, you will have this situation, and at the end of the beam, you will have this situation. At any location between the midspan and the end of the beam, you will have the compressive stresses less than 2FC, and you will not have any tensile stresses. You will have also compressive stresses in the lower part of the beam here at this location that will be greater than 0 and less than FC. Okay. Now let's look at the final situation where we have produced a situation by the application of by the eccentric application of force P, such that at any location all along the length of the beam is perfectly in a state of compression with no tension anywhere, which is the most favorable condition. So let's say instead of load Q 2Q, we now applied a load Q. Okay, once we apply load 2Q and the eccentricity is variable, you know that at the midspan before the application of the load, as was the case in the previous case, 0 2FC state of stress will be produced. But this time the load is not 2Q, it is Q, so it will be, instead of 2FC and 2FT, it will be plus FC and FT. So FC will become FC plus 0 will become FC, and 2FC minus FT will become FC. In the previous case, this was 2FC and 2FT. So 2FC plus 0 was 2FC, and 2FT minus 2FC is 0. In this case, instead of 2FC, this is FC and this is FT. So FC plus 0 is FC, and FT plus 2FC is FC. So you have perfect compression. State of stress is compressive in nature at the midspan of the beam. Now let's look at the end of the beam. At the end of the beam, you have FC and FC state of stress with 0 tensile and compressive stresses due to the load. So at the end also you have a compressive state of stress. So all along the length of the beam, you have perfect compression. The beam is perfectly in compression, which is a desirable situation for concrete. So with this concept of pre-stressing, we can completely avoid the need for reinforcing steel. We can also completely eliminate the deflections produced in the beam, because if we can pre-compress the beam, the deflections can also be minimized or completely eliminated. Tensile stresses can be completely eliminated or minimized. So these are the advantages of pre-stressing. Now, some important conclusions which can be drawn from the previous simple examples. Pre-stressing can control or even eliminate concrete tensile stresses for specified loads. We have seen in the previous example. Eccentric pre-stress is usually much more efficient than concentric pre-stress. This also we have demonstrated. And variable eccentricity is usually preferable to constant eccentricity from the viewpoints of both stress control and deflection control. And pre-stressing results in the overall improvement in performance of structural concrete used for ordinary loads and spans. Pre-stressing extends the range of application far beyond the limits for ordinary reinforced concrete, leading not only to much longer spans, because the problem with the reinforced concrete is that in longer spans you will have to use deeper members, and in the pre-stressed concrete there is no need of using deeper members, because the deflection can be completely eliminated. Tensile stressing can also be completely eliminated. With the economical member cross sections than previously thought possible, and permitting innovative new structural forms are also possible. Objectionable deflection and cracking, which would otherwise be associated with the use of non-pre-stressed reinforced concrete members at high stress, are easily controlled by pre-stressing. Okay, the next topic is before we discuss the next topic, let me discuss with you the mechanism through which we can produce these forces. Okay, let's say this is a beam with length LC, okay, and we are preparing, let's say we are preparing this beam in a lab, okay, and we have prepared a formwork for the beam such that we have placed a conduit in the mid depth of the beam in this manner, okay, and then we pass a steel wire or steel rod through this conduit, okay, and fix the rod at this end, one end of the beam here on this end. And then what we do is that we stretch the rod or the wire from the other end, here from this end, okay. And when we stretch this up to a certain length, then after the rod is being stretched, we also fix this end of the beam. So now the steel bar or the wire will tend to regain its original length, and in this effort, when the steel tends to regain its original length, it will start compressing the member. Okay, so the steel is although the steel in itself is in tension, it will compress whatever is bonded to steel. Okay, so now let's say we then pour concrete in the formwork. We then pour concrete in the formwork, and then we wait till concrete gains its full strength. And once the concrete gains its full strength, we release this wire from this location, from this end. So once we release this wire from this location, the steel and concrete are bonded together. Since the steel and concrete are bonded together, the steel will tend to regain its original length. The steel will tend to regain its original length, but it will not be possible for the steel to regain its original length due to the bond between steel and concrete. And when steel tends to regain its original length, it will keep on compressing concrete. So in this manner, a pre-compression state of stress will be produced in the concrete. I hope this is clear. If not, you can ask question.
Assalamu alaikum, sir. Zakaria.
Please.
सर इसमें जो आपने ये बताया कि इसमें हम ये कंड्यूट छोड़ेंगे ना सर, तो सर इसमें हम कंक्रीट पोर करेंगे कि नहीं, इसको खाली इस तरह छोड़ेंगे?
अच्छा, इसमें there are two methods. मैं आखिर में इसको डिस्कस करूंगा. इसमें एक होता है प्री टेंशनिंग एंड द अदर इज पोस्ट टेंशनिंग. इन प्री टेंशनिंग व्हाट वी डू इज कि हम इस स्टील में जो हम एंकर करते हैं एक साइड पे, ठीक है. प्री टेंशनिंग में कंक्रीट पोरिंग से पहले हम इसको स्टील को टेंशन में लाते हैं, और उसके बाद जब हम कंक्रीट पोर करते हैं और कंक्रीट अपना फुल स्ट्रेंथ अचीव कर ले, तो हम इधर से स्टील बार को छोड़ देते हैं, स्टील वायर को छोड़ देते हैं. ठीक है, पहले हमने मतलब इधर स्टील वायर इसमें से पास किया हुआ है और हमने इधर इसको स्ट्रेच भी किया हुआ है. तो इट हैज बीन स्ट्रेच्ड बाय सर्टेन लेंथ. लेकिन अभी टेंशन में है, कंक्रीट इसमें हम कर लेते हैं और स्टील और कंक्रीट के दरमियान बॉन्ड बन जाता है. लेकिन स्टील किस में है? स्टील टेंशन में है. ठीक है, जब हम स्टील को इधर से काट देते हैं, छोड़ देते हैं, तो स्टील क्या करेगा? स्टील अपने लेंथ को रिगेन करने की कोशिश करेगा, और जब ये रिगेन करने की कोशिश करेगा तो इन दिस एफर्ट इट विल कंप्रेस द कंक्रीट. सो इसमें हमने क्या किया कि वी हैव टेंशन द स्टील बिफोर कंक्रीट गेन्स इट्स फुल स्ट्रेंथ. ठीक है. अच्छा, दूसरी पॉसिबिलिटी ये है कि हम स्टील बार्स को स्ट्रेच करें. वी स्ट्रेच द स्टील वायर और बार, ओके, एंड देन we don't tension the steel. जस्ट हमने इसमें कंड्यूट रख दिया, ठीक है, और हमने इधर एंकर भी रख दिया, और इसके बाद हम क्या करते हैं कि हमने कंक्रीट पोर कर दिया, बट द स्टील हैज नॉट बीन स्ट्रेच येट. तो हम फिर क्या करते हैं कि इसमें जब हम कंक्रीट कर देते हैं तो स्टील और कंक्रीट के दरमियान अब ये कंड्यूट आ गया जो कि स्टील और कंक्रीट को बॉन्ड से रोकता है. ठीक है. इन द प्रीवियस केस let me say again, in the previous case there was no conduit. Just to stretch the wire, pour the concrete will be bonded to steel, and after the concrete gains its full strength, you cut the wire on one side which has been already stretched. So there is perfect bonding in the first case. In the second case there is a conduit, and due to the conduit you have passed the wire through the conduit, but since a conduit is present here, concrete will not be bonded to steel. Okay, so the steel is present here in the second case without bonding with concrete. Okay, so now when we pour concrete and we wait till concrete gains its full strength, then what we do is that since steel is not tensioned, but steel is present in the conduit and conduit is within the concrete beam, then we will anchor the steel on one end of the beam, on this end, through some anchoring mechanism, and we will stretch the steel wire on the other side through some jacks. Okay, and once this is sufficiently stretched, when the steel is sufficiently stretched, then the steel will be anchored on this end also, on this end. Okay, so through this anchoring mechanism on both ends, now the compressive force will be applied on the concrete beam, unlike the previous case where the compressive force was applied through bond between steel and concrete. So the previous case was the case of pre-tensioning, and this case, the second case, is the case of post-tensioning. In both these mechanisms, we can produce a pre-compression force in the beam. Okay, this we will discuss. I will finish some videos at the end. You will be able to see how pre-tensioning and post-tensioning is done.
Okay,
at the moment, please.
So the second question is that what type of material is what type of steel is used? Do we use
okay. That is what we are discussing. That is what we are discussing right now. Okay. Okay.
Excuse me, sir.
Please.
Sir, in the previous slides we discussed D and E case, sir, of pre-compression, sir.
Previous slide. This one.
Previous slide, sir. It's a picture, sir.
This one.
सर डी और ई केस इससे पीछे सर.
अच्छा, ओके
सर इसमें एसेंट्रिक ये हमने अप्लाई किया हुआ है लोड या कंसेंट्रिक है सर?
ये नहीं, ये तो वेरिएबल एक्सेंट्रिसिटी है. वेरिएबल एक्सेंट्रिसिटी, यू कैन सी द एक्सेंट्रिसिटी ऑफ दिस the cable or the wire which has been passed through this is varying in depth. with maximum eccentricity at the midspan. ये वायर जो केबल हमने इसमें से पास किया है ना, वो इस प्रोफाइल में हमने पास किया है, ठीक है। ये जो आपको डॉटेड लाइन नजर आ रहा है, तो वेरिएबल एक्सेंट्रिसिटी है, ठीक है। आगे कुछ वीडियोस हैं, उससे आप ये चीजें क्लियर हो जाएंगी इंशाल्लाह। Okay, now at the moment we are discussing that how what type of steel and what type of material shall be used. Okay, let's say now this is the length of the beam is LC. Okay, this is unstressed length of concrete. Okay, and we have a unstressed length of steel equal to LS. Okay, and LS, when LS is kept in this farm work, this is a case of, let's say, pre-tensioning. So we have a farm work, there is some anchoring mechanism on one side, and the length of the steel which we are using for pre-tensioning or pre-stressing is LS to this length. We stretch this to this length, which is the unstressed length of concrete beam. So when we stretch this LS by this amount, you know that steel bar cannot be stretched beyond its yield limit. If it is stretched beyond its yield limit, then it will permanently deform, permanently set, and the steel will not tend to regain its original length. So the steel must not be stretched even closer to its yield limit. It must be less than the yield limit. Okay, so let's say we are using a grade 40 steel. So you know that grade 40 steel, the yield strength can be very easily calculated. The yield strength of grade 40 steel will be equal to Fy, which is 40, and divided by 13 to the power 3, which is the modulus of elasticity. So Fy divided by E will give you the strain, the maximum strain that can be produced in a grade 40 steel, and you will have to produce strain less than the yield strain. Yes, less than the yield strain. Now let's say we produce a strain which is less than the yield strain of steel. Okay, and we then pour concrete. Once we pour concrete in the farm work, and after concrete gained its full length, we cut the wire from this side, and when we cut the wire from this side, which has already been stretched, the wire will tend to regain its original length, and in this effort, it will produce a pre-compression in the beam. Okay, so you know that when this force P is applied on the concrete, this force P will remain here forever. Okay, forever, because steel is perfectly bonded to concrete, and when steel is in tension and if it tends to regain its original length, it will keep on pressing concrete. Once this force P is applied, you know that when a force P is applied on a member, it will produce some elastic strain. You know this. You know that delta is equal to PL by AE when a force P is applied on a member having length L in area A and modulus elasticity of material is E. So delta is equal to PL by A will be produced, which is called elastic deflection, and it will produce elastic strains. Other than this, some shrinkage will also occur in the beam. Shrinkage will also reduce the length of the beam. Creep is a phenomena. You know that creep is also change in strain of the member, concrete member, at constant stress. So stress, the length of the beam will keep on decreasing due to shrinkage, due to creep, and also due to elastic strains. You know that this pre-compression force is present in the beam due to the stretching of steel bar. When concrete gains its, when the steel bar regains its original length, all of the pre-compression force will completely become zero, it will there will be no pre-compression force if strain in steel which was produced before the pouring of concrete becomes completely zero. So then there will be no pre-compression force. So when the steel is stretched before concrete is poured, and steel tends to regain its original length, it will keep on pushing concrete, in a pre-compression stress or pre-compression force will be present all along the length of the beam. However, if steel succeeds in regaining its original length, how is this possible? This is possible because we have cut the steel wire from this side, the steel bar from this side, and the steel will tend to regain its original length if creep and shrinkage occurs in the concrete beam, let's say, and the value of this creep, the change in length of the beam due to creep and shrinkage is such that the strain produced due to steel is completely eliminated. Then there will be no compression force left in the rod. Okay, like this. The strain in a grade 40 steel, the maximum strain in grade 40 steel, let's say, is 30 divided by 29,000, because as I said earlier, we cannot stretch the steel wire up to its yield limit. Otherwise, it's even closer to this. Otherwise, the steel will permanently set. So let's say the strain which is possible to be produced in a grade 40 steel is 30 divided by 29,000. So it is equal to 1.03 in 10 to the power minus 3. Okay. So, and the steel elongation delta we can calculate when this is multiplied by the length of the steel wire. It will be 1.03 in 10 to the power minus 3 ls. So it is the maximum delta that can be produced. That it is the maximum delta or change in length that can be produced in a grade 40 steel if it is to be used as a pre-compression steel. Then the sum of shrinkage and creep strain in the concrete is about 0.9 in 10 to the power minus 3, and the corresponding length change is this. Okay, this 0.9 in 10 to the power minus 3 is the change in the length of concrete, okay, due to shrinkage and creep. So it is the reduction in the length of, it is a reduction in the length of concrete beam or concrete member, which happens to shrinkage and creep alone, not due to the
Sir, sound clear nahi hai, sir.
strain. Elastic strain will be elastic strain will further reduce in the beginning before concrete pouring. By this amount, 1.03 in 10 to the power minus 3, there will be a 30 ksi stress present in the steel. Now, when concrete is poured and steel is cut after concrete gains its full length, the steel will tends to regain its original length, okay, and almost equal to the strain that we have produced before the pouring of concrete. And the stress which was in the beginning, the stress in the steel, the pre-compression stress in the steel, which was equal to 30 ksi in the beginning before the concrete pouring, is now finally reduced to 4 ksi. So this is almost a complete loss of the pre-compression stress of that extent, which will make the beam transverse loading. Okay, what is the conclusion from this discussion? Anyone?
Excuse me, sir.
What is the conclusion from this discussion?
Excuse me, sir.
Ji, please. Yes, please.
Sir, sound
Sir,
clear.
from the
nahi hai,
previous
sir.
slide, your
Bata
voice
diye,
was
sir.
not clear.
From the previous slide, my voice was not clear.
Sir, sound clear nahi hai, sir. Lagging ho rahi hai, sir.
जी
Yes, sir.
क्या हो रहा है?
सर स्लाइड नंबर 11 और 12 में आवाज
अभी ठीक है आवाज?
सर सर अभी ठीक है,
हाँ?
लेकिन 11 स्लाइड में कुछ समझ नहीं आया सर.
अच्छा ठीक.
अभी ठीक है सर, लेकिन 11 और 12 में बिल्कुल
चलिए
आवाज
स्लाइड
नहीं
में
है सर,
दोबारा
कट आ रही है. थैंक यू सर.
ठीक है, 11-12 स्लाइड में एक्सप्लेन करता हूँ. अच्छा ठीक है. जब मैं आपको ये बता रहा था कि आप अगर इस जिस तरह में कह रहा था कि ये एक आपके पास फार्म वर्क है बीम का, ठीक है, और उसमें आपने एक ग्रेड 40 स्टील पहले से ही फार्म वर्क में ऐसे लगा दिया कि एक साइड पे आपने उसके कर दिया.
सर साउंड क्लियर नहीं है सर.
और फिर आप इसको इधर भी स्ट्रेच करने के बाद स्ट्रेच पोजीशन में ही रहने दें. कंक्रीट पोर करें. जब कंक्रीट अपनी स्ट्रेंथ गेन करें एंड देन यू कट. अभी आपको आवाज आ रही है कि नहीं?
सर सेम प्रॉब्लम सर, योर वॉइस इज
सर कट आ रही है सर.
आप लोग की आवाज तो बिल्कुल ठीक आ रही है. Okay, can you hear me now?
Yes,
sir, now
sir.
it's better.
अच्छा, आप देखें ये फिगर स्लाइड 10. कैन यू सी द स्लाइड नंबर 10?
Yes sir.
Yes, sir.
Okay, so I was telling you that let's say there is a farm work, okay, which has been prepared for concrete pouring in order to produce a concrete beam. Before a concrete is poured, we stretch a wire, anchor the bar on one side and stretch it from the other side, and also anchor on this side, okay, and then we pour concrete. When concrete gains its full strength, we cut the wire on this side and also on this side. So when we cut the wire on both sides, the wire, the bar, which is in this case grade 40, let's say, this grade 40 steel will tend to regain its original length. Correct?
Yes sir.
Can you
Yes,
hear me
sir.
now?
Yes sir.
Yes,
grade
sir.
40 steel क्या करेगा? It will tend to regain its original length. हमने इसको स्ट्रेच किया है ना, तो जब स्टील और कंक्रीट का बॉन्ड बन जाएगा और हम इसको काट देंगे दोनों साइड से, तो राड क्या करेगा? राड कोशिश करेगा कि अपनी लेंथ को दोबारा हासिल कर ले, क्योंकि स्ट्रेच पोजीशन में है. तो उसमें जब ये इट विल टेंड टू रिगेन इट्स ओरिजिनल लेंथ, ये कंक्रीट को दबाएगा, ठीक है. और कंक्रीट को जब दबाएगा तो कंक्रीट, आपको पता है कि कंक्रीट की किसी भी मेंबर को आप कास्ट करें तो देयर विल बी change in the length of member, a reduction. I mean, reduction in the length of member due to creep and shrinkage. You know shrinkage phenomena. that there is in shrinkage, there is a reduction in the volume of concrete. You know this, okay? So जब वॉल्यूम ऑफ कंक्रीट कम होगा तो इसका मतलब है कि कंक्रीट की लेंथ, कंक्रीट की बीम की लेंथ कम हो जाएगी। जब कंक्रीट की बीम की लेंथ कम होगी तो स्टील जो पहले से स्ट्रेच था उसकी लेंथ भी कम हो जाएगी, ठीक है? एंड यू नो द क्रीप फिनोमेना, दैट क्रीप इज चेंज in the length of a concrete member at constant load or constant stress. तो कुछ लेंथ जो है वो श्रिंकेज की वजह से कंक्रीट बीम की कम हो जाएगी और कुछ क्रीप की वजह से कम हो जाएगी, और स्टील भी यही चाहता था कि उसकी अपनी ओरिजिनल लेंथ आ जाए। तो अगर क्रीप और श्रिंकेज की वजह से जो चेंज कंक्रीट की बीम में आ गया, यानी जो रिडक्शन आ गई, वो स्टील के उस लेंथ के से जो ओरिजिनल स्ट्रेचिंग से पहले थी उसके बराबर हो गई, तो स्टील में कोई स्ट्रेस नहीं रहेगा। Is that okay?
Yes sir.
Yes sir.
ठीक है ना? अब हम देखते हैं न्यूमेरिकली कि द मैक्सिमम, अब मैंने आपको ये बताया कि स्टील मस्ट नॉट बी स्ट्रेच्ड टू द यील्ड लिमिट, इवन क्लोजर टू द यील्ड लिमिट। तो अगर ग्रेड 40 का स्टील हम इस्तेमाल कर रहे हैं तो ग्रेड 40 स्टील में लेट्स से द मैक्सिमम स्ट्रेस व्हिच इज पॉसिबल बिकॉज 40 is its yield stress or yield strength. So let's say the maximum stress that we can produce in grade 40 is 30 KSI. So 30 divided by 29,000 will give us the maximum strain which can be produced in a grade 40 steel. जब हम ये करते हैं तो हमारे पास ये अगर स्ट्रेन आ गया तो डेल्टा, द मैक्सिमम डेल्टा इस, ये जो हम स्ट्रेच करेंगे ना स्टील को, इसको मैं डेल्टा कहता हूँ। तो वो डेल्टा किसके बराबर होगा? लेंथ ऑफ द स्टील और स्ट्रेन जो कि मैक्सिमम उसमें प्रोड्यूस हो सकती है, तो 1.03 × 10⁻³ LS। अब ये तो कंक्रीट पोरिंग से पहले हमने इतना डेल्टा उसमें प्रोड्यूस कर दिया और हमने उस स्टील को उधर बांध दिया। अब जब हम कंक्रीट के फार्म वर्क में कंक्रीट पोरिंग करेंगे और कंक्रीट अपनी फुल स्ट्रेंथ को अचीव कर लेगा, तो उसके बाद जब हम स्टील बार को दोनों साइड से काट देते हैं और स्टील बार बांड अपने कंक्रीट और स्टील बार के बांड की वजह से अब कंक्रीट को दबाना शुरू करेगा। लेकिन इस दौरान अगर कंक्रीट श्रिंकेज और क्रीप की वजह से अपनी लेंथ को कम करने में कामयाब हो गया, कंक्रीट श्रिंकेज और क्रीप की वजह से उसकी लेंथ कम होगी आहिस्ता आहिस्ता, तो स्टील की लेंथ भी कम होगी। तो क्रीप और श्रिंकेज की वजह से कलेक्टिवली जो स्ट्रेन आता है वो 0.9 × 10⁻³ के। दिस इज कंफर्म फ्रॉम द एक्सपेरिमेंट्स कि 0.9 × 10⁻³ जो है इतना स्ट्रेन कंक्रीट के मेंबर में आ जाता है कुछ अरसे के बाद। अच्छा, इसको जब आप कंक्रीट के लेंथ से मल्टीप्लाई करेंगे 0.9 × 10⁻³ तो इतना डेल्टा वापस आ जाएगा। डेल्टा एस में से ये डेल्टा निकल जाएगा। डेल्टा एस तो पहले प्रोड्यूस किया था, ये डेल्टा सी तो उसके अपोजिट है, तो नेट हमारे पास जो डेल्टा रह जाएगा वो होगा 1.03 - 0.9 × 10⁻⁻। हमारे पास इफेक्टिवली इतना डेल्टा रह जाएगा। और जाहिर है कि जब हमारे पास इतना डेल्टा रह जाएगा तो जो स्ट्रेन है, स्ट्रेन भी कम हो गया, और इस स्ट्रेन को अगर हम ई से मल्टीप्लाई करें तो हमारे पास अब हमें पता चल जाएगा कि हमारे पास फाइनली स्ट्रेस कितना रह गया। तो द फाइनल स्ट्रेस, द इनिशियल स्ट्रेस वाज 30 KSI, बट आफ्टर द क्रीप एंड श्रिंकेज the reduction in concrete member due to creep and shrinkage, the effective stress is 4 KSI. ठीक है, इनिशियली जो स्ट्रेस 30 KSI था वो आखिर में 4 KSI रह गया, क्योंकि जो स्टील में हमने स्ट्रेचिंग की थी वो स्ट्रेचिंग कंप्लीटली तकरीबन खत्म हो गई क्रीप और श्रिंकेज की वजह से, क्योंकि कंक्रीट की बीम की लेंथ कम हो गई। तो स्टील की लेंथ भी कंक्रीट के बीम के साथ आहिस्ता आहिस्ता कम होगी, और ये मुमकिन है कि स्टील में जितना स्ट्रेच हमने प्रोड्यूस किया था वो कंक्रीट बीम की रिडक्शन के साथ कंप्लीटली खत्म हो जाए। तो क्रीप और श्रिंकेज की वजह से जितना स्ट्रेन प्रोड्यूस होगा, अगर हम उसको इनिशियल स्ट्रेन से माइनस करेंगे तो हमारे पास बहुत कम स्ट्रेन रह जाएगा। और इसके साथ साथ इसके बाद इलास्टिक शार्टनिंग भी बीम की होगी, क्योंकि जब बीम को ये स्टील रॉड प्रेस करेगा तो इसमें इलास्टिकली कुछ शार्टनिंग भी होगी, जो कि आप लोग कई दफ़ा मालूम कर चुके होंगे अपने अंडरग्रेड कोर्सेज में, डेल्टा इज इक्वल टू PL/A इक्वेशन से। जब P लगा हो किसी मेंबर पर तो डेल्टा उसमें आएगा PL/AE के हिसाब से, वो भी स्ट्रेन को कम करेगा। तो अगर उसको हम डिस्कस न भी करें तो ग्रेड 40 स्टील का फाइनल जो स्ट्रेस होगा वो 4 KSI होगा, या ये भी तकरीबन खत्म हो जाएगा। इसका मतलब ये है, व्हाट डू वी कंक्लूड फ्रॉम दिस डिस्कशन? Any one of you? What is the conclusion of this discussion?
सर स्टील में जो स्ट्रेस हमने प्रोड्यूस किया था वो स्ट्रेस वो कंक्रीट में ट्रांसफर हो जाएगा सर.
No, वो तो कंक्रीट में ट्रांसफर हो गया, लेकिन फाइनली व्हाट हैपेंड फाइनली? Anyone else? The conclusion is that grade 40 steel cannot be used for this pre-stressing, because if we use this, finally we don't have any pre-stressing force left. ठीक है, क्योंकि ये pre-stressing force उस वक्त अप्लाई होगा जब स्टील स्ट्रेच्ड कंडीशन में हो. लेकिन अगर स्टील की ये स्ट्रेच कंडीशन खत्म हो जाए तो प्रीस्ट्रेसिंग फोर्स भी खत्म हो जाएगा. और वो स्टील की स्ट्रेच कंडीशन उस वक्त खत्म होगी जब कंक्रीट का मेंबर आहिस्ता आहिस्ता अपनी लेंथ को कम करके स्टील के स्ट्रेचिंग को भी खत्म करेगा. तो स्टील की स्ट्रेचिंग कंक्रीट के बीम की लेंथ के साथ रिडक्शन में आहिस्ता आहिस्ता वो खत्म हो जाए, क्योंकि स्टील में जो स्ट्रेचिंग है वो तो उसकी ओरिजिनल लेंथ को हमने खींचा हुआ था, स्ट्रेच किया हुआ था, और उस स्ट्रेच पोजीशन में वो कंक्रीट में स्ट्रेस ट्रांसफर कर रहा था. अगर वो स्ट्रेच पोजीशन में ना हो तो कोई स्ट्रेस प्रोड्यूस नहीं करेगा, कंक्रीट के बीम को कंप्रेस नहीं करेगा. तो ग्रेड 40 स्टील जो है इट्स नॉट, इट कैन नॉट बी यूज्ड. वी मस्ट हैव टू यूज हाई स्ट्रेंथ स्टील. लेट्स से नाउ वी डिस्कस 150 KSI steel instead of 40, 60. We use 150 high strength steel, 150 KSI. In 150 KSI steel, -3, and the delta that can be produced is 5.17 10 to the power -3, and the effective steel stress FAC, which is left after, because creep and shrinkage strength will remain the same. So जब इसको आप ज्यादा किसी भी वायर या बार को आप जितना ज्यादा स्ट्रेच कर सकेंगे और जितना स्ट्रेच ज्यादा होगा, प्रोवाइडेड कि उसका ई मॉडुलस ऑफ इलास्टिसिटी वही हो जो कि ग्रेड 40 और 60 का है, तो जब आपका स्ट्रेन ई के साथ मल्टीप्लाई होगा तो ज्यादा स्ट्रेस प्रोड्यूस कर सकेगा. तो अब 5.17 minus 0.9 10 to the power -3 into 29 10 to the power -3, still you are left with 124 KSI after creep and shrinkage. तो क्रीप और श्रिंकेज की वजह से जो रिडक्शन कंक्रीट के बीम में हो गई, उसके बाद भी आपके पास 150 KSI अगर इनिशियल स्ट्रेस था, तो क्रीप और श्रिंकेज के बाद 124 KSI हमारे पास स्ट्रेस फिर भी रह गया. इसमें से थोड़ा मजीद कम हो जाएगा तो फिर भी हमारे पास काफी स्ट्रेस कंक्रीट में रहेगा, कंक्रीट बीम में, और कंक्रीट बीम विल रिमेन इन प्री compression state of stress. The conclusion from this two slides is, in the pre-stressing members, the ordinary reinforced concrete, the reinforcing steel used in reinforced concrete cannot be used for pre-stressing. What are generally the types of high strength steel being used in the pre-stress members? There are three types. One are called as wires. You must have seen wires for use for pre-stressing. Wires are normally bundled in groups of up to about 50 individual wires to produce pre-stressing tendons of the required strength. Wire जो है मतलब एक तार की शक्ल में आप लोगों ने देखे होंगे, wires of steel wires. उसको स्ट्रेच करते हैं, anchored on one side and then stretch on the other side, और फिर उसको काट दिया जाता है, तो वो वायर्स जो है बांड के जरिए से कंक्रीट में प्री कंप्रेशन फोर्स ट्रांसफर कर देता है. ठीक है, वायर्स एक इस्तेमाल हो सकता है, 2 3 4 5 तकरीबन 50 वायर्स भी इकट्ठे खींच के कंक्रीट में ये प्री कंप्रेशन फोर्स ट्रांसफर करने के लिए इस्तेमाल हो सकते हैं. स्ट्रैंडेड केबल, जिस तरह स्टील की एक रस्सी आप समझ लें, ये ऐसी है, आपने देखे होंगे प्री स्ट्रेसिंग केबल्स. ये इसमें ऐसे होता है कि एक दरमियान में एक वायर होता है और बाकी 6 वायर जो है उसके इर्द गिर्द लपेट लेते हैं. तो जिस तरह रस्सी हम बनाते हैं ना, इस तरह स्टील की एक रस्सी बनाती है. 6 वायर्स आर वाउंड अराउंड 7 ऑफ स्लाइटली लार्जर डायमीटर. तो आपने स्ट्रैंड्स काफ़ी सारे देखे होंगे. और एलॉय स्टील बार्स भी, अगरचे इनका इस्तेमाल बहुत कम है, लेकिन एलॉय स्टील बार्स आर आल्सो यूज्ड. नॉर्मली केबल्स एंड वायर्स आर यूज्ड फॉर स्ट्रेसिंग विद वेरी हाई स्ट्रेंथ. और इसकी जो डायमीटर्स अवेलेबल हैं, जनरली तो ये अवेलेबल है, लेकिन ज़्यादा भी अवेलेबल हैं. प्री स्ट्रेसिंग वायर में तकरीबन 5 to 7 मिलीमीटर के वायर्स अवेलेबल हैं, स्ट्रैंड में 0.6 to 15 मिलीमीटर के केबल्स अवेलेबल हैं, और एलआई स्टील बार्स में 19 to 35 मिलीमीटर के अवेलेबल हैं प्लेन में, और डिफार्म में 16 to 32 मिलीमीटर के अवेलेबल हैं जनरली, लेकिन इससे ज़्यादा भी हो सकते हैं। स्ट्रैंड्स में तकरीबन 25 मिलीमीटर 32 मिलीमीटर तक भी स्ट्रैंड्स मार्केट में अवेलेबल हैं, लेकिन जनरली वो अवेलेबल नहीं होते। एंड द स्ट्रेंथ, इसमें ग्रेड्स अगर राउंड वायर्स को आप देख ले तो अनलाइक ग्रेड 1460 जो है मच हाई यील्ड स्ट्रेंथ 235 to 14 to 50 KSI. This is FY, yield strength for round wires, and yield strength for strands. There are two types, 215 to 720. A third one is 300, recently being produced in factories, but is not recognized by ASTM A41. And the elastic steel bars are produced in 145 KSI and 160 KSI. Stress strain curves for pre-stressing steel or high strength steel, you can see that the stress strain curve for high strength steel are quite different than what we have seen in the reinforcing grade 14, grade 60 steel. And the yield strength is not very clear. If you test a high strength steel wire in the lab, then the location of the yield strength on the curve is not very clear. And for this purpose, we draw a line at the strain of 0.7%. You can see that this is a graph of stress to strain. Okay, so you can see the stress strain curve for a grade 60 steel, and this is for 150 bar, this is for 160 bar, this is for 250, grade 250 wire, and grade 250 strand and grade 270 strand. Okay, so the yield strength is somewhat arbitrarily defined as the stress at a total elongation of 1% for strand and wire and 0.7% for elastic. So generally what we do is that we draw a line at 1% strain parallel to y-axis, and wherever it meets the stress strain curve for that particular steel wire or strand is taken as the yield strength of steel. Okay, it is very important to actually determine the yield strength in the lab, because as I said quite a few times, that the steel must not be stretched even closer to its yield strength, because then the steel will permanently set. So it is important to accurately calculate the yield strength of steel from a lab test. And the procedure of ASTM for this is that once the stress strain curve is drawn, and the stress strain curve is drawn for a particular steel, then a line parallel to y-axis at 1% strain is drawn, and wherever it meets the stress strain curve of that particular steel is taken as the yield strength. Okay, for wires and cables, and for steel, allied steel, it is 0.7%. The pre-stressing steels have significantly less ductility as compared to grade 14, 60. You can see this highly ductile, but we don't need ductility in this case, because we don't allow our pre-stressed members to be subjected to tensile stresses, and therefore ductility is not an objective to be achieved in pre-stressing pre-stressed members. Modulus of elasticity of pre-stressing steel. For unbonded strain, it is 26,000 psi. For bonded strain, it is 27. For smooth round wire, this is 29 ksi. And for elastic bar, it was 27 10⁻⁶. Relaxation is a phenomena which occurs in steel at constant stress constant stretching. When pre-stressing steel is stressed to the levels that are customary, that are very customary means that are very common during initial tensioning and at service loads, it exhibits a property known as relaxation. Relaxation is defined as the loss of stress in stressed material held at constant length. The same basic phenomena is known as creep when defined in terms of change in strain of material under constant stress. You know about creep. Creep is a phenomena which occurs in concrete. And creep is change in strain, either increase or decrease in length. If the load is a compressive load, then there will be reduction in the length of concrete member with time at constant load. Okay, because with the increase in load, whatever change in length occurs, that is called elastic shortening or elastic elongation. Elastic shortening if the force applied is a compressive force. If the force is tensile force, then it will elongate. It will produce elongation. And this elongation will keep on increasing with the increase in the tensile stress. However, if tensile stress or tensile load is kept constant, then due to creep, there will be an increase in the concrete member at constant tension. Now, on the other hand, if concrete member is in compression, and if there is a force P which is kept constant for a long duration, this force P, even though it is constant, will produce delta in concrete, which is not the elastic shortening that will be produced due to creep, and the change in strain of concrete material under constant load or stress is known as creep. So quite opposite to this, a phenomena known as relaxation occurs in steel. When steel is stretched and it is left for a long time in the stretched position. So you know that the stretching will produce a strain. The stretching will produce strain in steel. Okay, and if this strain is constant, so the strain multiplied by the modulus of elasticity equal to stress. The stress in steel should remain constant. However, this does not happen practically. Practically, even at constant strain, if steel is kept for a long duration in a stretched position, then even though the strain remain constant, there is a loss in stress. Though there is no loss in strain. Even though there is no loss in strain, there will be loss in stress, and this is a property of steel which is called as relaxation. So if there is a loss in stress due to relaxation, then the pre-compression stress which was applied in the beginning for a pre-stress member will be lost to some extent, and the pre-compression force will also be reduced, and this must be taken into account in the designing of pre-stressed concrete members. Okay, to be specific, if a length of pre-stressing steel is stressed to a sizable fraction of its yield strength, say 80 to 90%, and held at constant strain between fixed points, such as the ends of the beam, the steel stress FP will gradually decrease from its initial value FPI because of this property of steel known as relaxation. And this relaxation, loss in relaxation can be calculated from these two equations. A satisfactory estimate for ordinary stress relieved strain and wires can be obtained from equation 1, which was derived from more than 400 relaxation tests of up to 9 years duration. If you look at this equation, FP is the final stress after relaxation, FPI is the initial stress applied, log of T is the time duration, okay, and T is time in hours. FP is also this FP, and FPY is the yield strength minus 0.55. So if log of T is substituted in this equation, where T is in hours, So let's say log of 400, after 400 hours, 400 divided by 10, and let's say FP, and FP will be calculated. And FPI, if FPY is, let's say, 250 KSI, and if FPI is 200, so you will substitute here 200, here 250, and log of 400, and FP can be then, the equation can be simplified for FP, and FP can be calculated, which will give us the stress in steel after relaxation. So this also shall be known to us. Whatever stress is lost in steel due to relaxation, this must be known to us for the designing of pre-stressed member. As you know that pre-stressing involves a lot of pre-compression force transferred to concrete, so concrete must have a good compressive strength also. For this reason, we generally use good high-strength concrete in our pre-stress construction. Although the exact definition of high-strength concrete is arbitrary, the term generally refers to concrete having uniaxial compressive strength in the range of 8,000 to 15,000 psi or higher. Okay, so if a concrete is 8,000 psi or higher, then it will be called as high-strength concrete. Okay. Such concretes can be made using carefully selected but widely available cements, sand, and stone, certain admixtures including high-range water-reducing, superplasticized fly ash, silica fume, plus very careful quality control during production. You must have studied these things in your concrete course. The advantages of high-strength concrete are that high-strength concrete has a higher elastic modulus than the low-strength concrete, so that loss of pre-stress force resulting from elastic shortening of the concrete is reduced. Creep and shrinkage losses are also very low. High bearing stress in the vicinity of tendon anchorage for post-tension members are more easily accommodated, because especially in the post-tension members, when the anchorage devices are used on both ends of the beam, so there is a substantially high possibility of crushing of concrete in the vicinity of those anchoring devices. So for this purpose, high-strength concrete is good to be used. In the case of pre-tensioning elements, higher bond strength results in a reduction of the development depth required to transfer pre-stress force from the cables to the concrete. So high-strength concrete is good for this too. Finally, concrete of higher compressive strength also has a higher tensile strength, so that the formation of flexure and diagonal tension crack is delayed. These are typical stress strain curves for high-strength concrete. You can see that high-strength concrete is more brittle as compared to low-strength concrete. Although concrete is brittle in nature as compared to steel, but if we compare low-strength concrete to high-strength concrete, then high-strength concrete is brittle as compared to low-strength concrete. But it is not of significance for us, because we never use concrete for ductility in our structures. Okay, now methods of pre-stressing. This needs your attention now. Although there are many methods, but the two methods, all the methods can be divided into two methods: pre-tension and post-tensioning. Pre-tensioning. In pre-tensioning method, the strands are tensioned over the full length of the casting bed at one time, after which a number of individual members are cast along the stressed tendon. When the jerking force is released, the pre-stress force is transferred to each member by bond, and the strands are cut free between members. Okay, this is a typical assembly used in pre-tensioning. Pre-tensioning and post-tensioning are two techniques used in pre-stressing. If you have ever visited a prefabricated factory, you would have seen such kind of arrangement in a prefabricated factory, where pre-cast slabs and pre-cast girders are produced. Okay, this is an assembly for producing one girder at one time. You can see an anchorage here on this side. So the wire is anchored on this side, and then the wire is passed through the formwork, and it is with the help of a jack, it is stretched on this side, and then it is left in the stretch position. Then the concrete is poured in the formwork. Then when concrete gains its full strength, the wires are cut from this side, and also it's cut from this side. Okay, and then when the wire tends to regain its original length, it applies the pre-compression force as explained earlier. Okay, if you want to apply a pre-compression force with variable eccentricity, then the wires is held down due to some, with the help of some arrangement in this position. Okay, the wire is stretched in this manner, and then when concrete gains its original length, the wire is cut from this side and this side, and the force is transferred to concrete with a variable eccentricity. Okay, if please. Yes.
सर ये फर्स्ट केस में जो आप बता रहे हैं ना सर, तो इसमें जब हम वायर को कट करते हैं तो ये सर उसमें ये बॉन्ड कंक्रीट और वायर में इतना बॉन्ड होगा सर कि वो उसको रेजिस्ट कर सके, इस में इसको तो हमने एंकर नहीं किया था ना सर एंड पॉइंट पे।
नहीं एंकर नहीं किया है वो। आपको डेवलपमेंट लेंथ तो पता है ना?
यस सर।
तो डेवलपमेंट लेंथ इतनी होनी चाहिए कि ये ट्रांसफर करे। आपको डेवलपमेंट लेंथ आपने पढ़ लिया हुआ है कि वो किस तरह वेरी करता है। तकरीबन ऐसे रफली स्पीकिंग 40 टाइम्स द डायमीटर ऑफ द बार या 50 तकरीबन इतना होता है। तो अगर 100 टाइम्स डायमीटर ऑफ द बार भी हो और आप 1 इंच का बार इस्तेमाल, मतलब 1 इंच का वायर या 1 इंच का केबल इस्तेमाल कर, तो आपको 100 इंच चाहिए, ठीक है, जो कि तकरीबन 8 फुट बनता है। तो 8 फुट तो इसके लिए आराम से अवेलेबल होता है। यानी आप 10-15 फुट का बीम बनाते तो उसमें तो डेवलपमेंट बहुत ज्यादा होती है, तो उसमें इशू नहीं होगा, ठीक है।
नहीं लेकिन सर ये जब होगा तो सर इसको जब हम दोबारा काटेंगे ना सर, तो ये तो कंप्रेस होगा ना, तो अगर सर इसमें ये बॉन्ड तो ये सर कंक्रीट और रीइंफोर्समेंट में तो सर ये इतना मजबूत नहीं होता कि वो उसको रेजिस्ट कर सके सर। इसमें स्लिपिंग जो है वो अकर नहीं होगी सर?
स्लिपिंग अगर होगी अगर डेवलपमेंट लेंथ से ये लेंथ कम है। अगर डेवलपमेंट लेंथ के बराबर है तो फिर नहीं होगी।
ओके सर, ओके।
डेवलपमेंट लेंथ विल इंश्योर। अगर ये लेंथ बहुत कम है तो ये स्टील और कंक्रीट के दरमियान स्लिप हो जाएगा। लेकिन अगर कंक्रीट बीम की लेंथ इतनी है कि उसमें डेवलपमेंट लेंथ की रिक्वायरमेंट पूरी हो जाती है तो देन स्लिप विल नॉट अकर।
सर ये डिफॉर्म बार्स होंगे सर उसमें, तो फिर ये तो शेप डिफॉर्म होता सर, तो उसमें अगर रेजिस्टेंस तो मे भी उसमें ज्यादा हो। लेकिन सर अगर हम केबल की बात करें तो सर केबल जो जनरली यूज होते हैं वो तो सर बहुत ज्यादा स्मूथ होते हैं, तो
स्मूथ के लिए डेवलपमेंट लेंथ की रिक्वायरमेंट भी ज्यादा है ना। ये तो नहीं है कि बांड उसके दरमियान बांड तो बनेगा ना कि नहीं बनेगा?
बनेगा सर। जब
बांड बन जाएगा तो फिर डिपेंड इस पे करता है कि लेंथ कितनी है। डिफॉर्म बार के मुकाबले में स्मूथ वायर की लेंथ काफी ज्यादा होनी चाहिए फॉर स्ट्रेस ट्रांसफर, ठीक है ना। तो उतनी लेंथ हम प्रोवाइड करेंगे। ये डिजाइन में ये इन चीजों का ख्याल रखते हैं।
ओके सर,
ठीक है। आपने कभी तैयार छतों वाली कोई फैक्ट्री विजिट की हो तो उसमें आपने देखा होगा सिंपल वायर्स इस्तेमाल, स्मूथ वायर्स इस्तेमाल करते हैं, डिफॉर्म्ड वायर्स इस्तेमाल नहीं करते, स्मूथ वायर्स। और वो सिर्फ कंक्रीट और स्टील के बॉन्ड की वजह से ये स्ट्रेस ट्रांसफर करते हैं, ठीक है। दिस इज अ बेड, टिपिकल बेड यूज्ड इन ए प्री कास्ट फैक्ट्री। प्री कास्ट फैक्ट्री अगर आप जाएं तो इस किस्म की आप अरेंजमेंट देख लेंगे जिसमें एक टाइम में काफी सारे बीम्स कास्ट करते हैं। So a wire is stretched from one end to another end through help of a jack. It is then kept in a stretched position. Concrete is poured in the formwork, and then the steel wire is cut here, all these locations. Okay, here, and then after cutting the steel wire, only due to bond between steel and concrete will transfer the pre-compression force to the concrete member. Correct? Okay. ठीक है जी।
यस सर।
यस सर।
These are typical pre-tensioning girders. अगर आप देख सकते हैं इधर जो वायर्स हैं, यू कैन सी द वायर्स। आप अगर किसी तैयार छतों वाली फैक्ट्री में चले जाएं ना, और आपने कभी ये गर्डर जो आई शेप का गर्डर होता है जो आमतौर पर तैयार छतों में लोग इस्तेमाल करते हैं, तो उसमें आप ये ख्याल करें कि उसमें जो उसका जो पार्ट उसका प्री कंप्रेस किया होता है, यानी जिधर आपके वायर्स होते हैं ना केबल, वो जरूर नीचे रखेंगे। अगर आपने उल्टा रख दिया, और जो तैयार छतों वाली फैक्ट्री वाले लोग होते हैं उनको तो पता होता है, लेकिन अगर किसी ने गलती से उसको नीचे किया तो वो फौरन ही फेल हो जाएगा। तो उसमें जो नीचे साइड होता है जिसको हमने प्री कंप्रेस किया उसको नीचे लाना होता है। आप अगर उसको अभी जरा गौर से देख लें, किसी भी फैक्ट्री को विजिट करें तो आपको अंदाजा हो जाएगा। The advantage of pre-tensioning. This method is well suited to the mass production of beams using the long line method of pre-stressing. And pre-tensioning is particularly economical method of pre-stressing, not only because the standardization of design permits reusable steel or fiberglass forms, but also because the simultaneous pre-stressing of many members at once results in great saving of labor. In addition, expensive and encourage hardware is eliminated. सबसे बड़ा एडवांटेजेस जो इस मेथड का है वो ये है कि जब आप एंकरेज डिवाइसेस के जरिए से ये प्रीस्ट्रेसिंग फोर्स ट्रांसफर करेंगे तो एंकरेज डिवाइस की भी काफ़ी कीमत होती है, वो एक्सपेंसिव डिवाइसेस होते हैं और ये सिर्फ बांड की वजह से स्ट्रेस ट्रांसफ़र कर लेते हैं, तो इसमें ये एक एडवांटेज है। और ये मेथड ज़्यादातर फैक्ट्रीज़ में जो गर्डर्स और स्लैब्स तैयार होते हैं उनके लिए ज़्यादा मुफीद है, क्योंकि एक वक्त में ज़्यादा इसमें प्रीस्ट्रेसिंग मेंबर्स प्रोड्यूस हो सकते हैं, ठीक है ना। लेकिन साइट के लिए ये मेथड इसलिए मौजूद नहीं है कि आप स्टील को स्ट्रेच रखेंगे काफ़ी दिनों तक, जब तक कंक्रीट अपना स्ट्रेंथ अचीव न कर ले, तो उस वक्त आपने इसको स्ट्रेच पोजीशन में रखना है, जेक भी उधर इंगेज रहेगा और हो सकता है कोई नुकसान हो जाए। तो इसके लिए साइट के लिए मौजूद नहीं है, लेकिन फैक्ट्री के लिए ये अच्छा मेथड है, क्योंकि फैक्ट्री में तो किसी और को आने की इजाज़त नहीं होगी, तो अगर स्टील वायर स्ट्रेच भी है 10-12 दिनों तक तो उसमें कोई नुकसान नहीं है। पोस्ट टेंशनिंग, जी प्लीज
सर इसमें ये काइंडली दोबारा वो बात बताए सर, जो अभी आपने वो नीचे रखने वाली की है कि जो हमने जो पोर्शन स्ट्रेस किए तो उसको नीचे रखेंगे।
नीचे नहीं रखेंगे, मैंने कहा कि जो स्ट्रेच हम करेंगे ना, तो स्ट्रेच करने के बाद तो हम वायर्स को उसी पोजीशन में छोड़ेंगे, स्ट्रेच पोजीशन में छोड़ेंगे, तो जेक भी उधर होगा, क्योंकि जेक के जरिए से आप उसको स्ट्रेच करेंगे ना, ठीक है। तो उसमें जब स्टील वायर काफ़ी अरसे तक स्ट्रेच पोजीशन में हो और आप इसको साइट में इस्तेमाल करेंगे, तो चांसेस इसके हैं कि कोई आके इसको छेड़ दे और उसका नुकसान हो जाए, क्योंकि तो बहुत ज़्यादा हाई टेंशन में होता है, अगर वो काट देंगे तो ये बुलेट की तरह वो शूट करता है फिर, तो इसलिए साइट के लिए मौजूद नहीं है। लेकिन फैक्ट्री के लिए इसलिए मौजूद है कि फैक्ट्री में तो कोई बाहर का आदमी नहीं आता, फैक्ट्री के लोग होते हैं, उनको पता होता है अगर जेक से आप उसको स्ट्रेच करेंगे और 10-12 दिनों तक स्ट्रेच पोजीशन में रहे और उसके बाद आप इसको काट दे तो कोई मसला नहीं है। लेकिन साइट में आप इतने अरसे तक इसको स्ट्रेच पोजीशन में नहीं रख सकते, इसी वजह से साइट में हम पोस्ट टेंशनिंग करते हैं। अगर साइट में हमें गर्डर्स, जिस तरह अगर आपने ब्रिजेस में गर्डर्स, आपने इस हमारा जो BRT प्रोजेक्ट है इसमें काफ़ी सारे जो ओवरहेड ब्रिजेस हैं आपने उसमें देखा होगा कि इसमें मुख्तलिफ किस्म के गर्डर्स इस्तेमाल होते थे, लेकिन वो उधर ही साइट पर पोस्ट टेंशनिंग करते हैं। पोस्ट टेंशनिंग का मैं तरीका आपको बताता हूँ किस तरह करते हैं। पोस्ट टेंशनिंग में यूजुअली hollow conduits containing the unstressed tendons and wires are placed in the beam forms to the desired profile before pouring the concrete। क्या करते हैं कि इसमें फॉर्म वर्क में आप उसको पहले से ही एक कंड्यूट में से अपने वायर्स या केबल पास कर ले और उसको अनस्ट्रेस्ड छोड़ दें, एंड देन क्या करेंगे आप, उसके बाद कंक्रीट पोर करेंगे, और अभी हमारा कंड्यूट में जो वायर्स और केबल्स पड़े हुए दे आर इन अनस्ट्रेस्ड पोजीशन, ठीक है, अनस्ट्रेस्ड पोजीशन में है। तो व्हेन द कंक्रीट हैज गेन्ड इट्स सफिशिएंट स्ट्रेंथ, कंक्रीट फिर पोर करेंगे और कंक्रीट जब अपना स्ट्रेंथ अचीव करे, द कंक्रीट बीम इटसेल्फ इज यूज्ड टू प्रोवाइड द रिएक्शन फॉर स्ट्रेसिंग जैक। उसके बाद हम क्या करते हैं कि when the tendon anchored by special fittings at the far end of the member, एक साइड पे हम एक प्लेट लगाते हैं और उसके साथ उस वायर्स के साथ वेजेस होते हैं, आपको मैं तस्वीर में दिखाता हूँ आगे, उसके साथ हम उस साइड पे उसको एंकर कर देते हैं। और दूसरा साइड जिसमें कंड्यूट में हमने तो केबल पहले से गुजारे होते हैं, कंक्रीट ने अपनी स्ट्रेंथ भी अचीव कर ली है, अब उधर से हम जेक से उसको खींचना शुरू कर देते हैं, और जब रिक्वायर्ड स्ट्रेचिंग हम प्रोड्यूस कर लेते हैं तो दूसरे साइड पर भी हम एक एंकरिंग डिवाइस लगा लेते हैं, उसमें हम काटते नहीं है बल्कि दोनों साइड पर एंकरिंग डिवाइस, और ऑल अलोंग द लेंथ ऑफ द बीम देयर इज नो बॉन्ड बिटवीन कंक्रीट एंड स्टील। सो इसको हम कहते हैं अनबॉन्डेड पोस्ट टेंशनिंग केबल्स एंड स्ट्रैंड, अनबॉन्डेड। लेकिन ये भी मुमकिन है कि जब आप दोनों साइड पर एंकरिंग डिवाइसेस लगा दें तो आप कंक्रीट बीम के साइड से उसमें इंजेक्शन आप उसमें से ग्राउटिंग कर दें, और ये स्ट्रेस जो आपके पास वायर्स या केबल्स है यू बॉन्ड दिस टू कंक्रीट, ये भी मुमकिन है, दिस इज पॉसिबल, एंड इन दैट केस इट विल बी कॉल्ड एज बॉन्डेड केबल्स एंड बॉन्डेड tendons. इस तरह से होगा. This is an anchoring device with this is the desired profile which is to be used after the design. Okay, and this is the jig. When concrete is poured inside the formwork, the steel wires or tendons, they are in unstressed condition. Then after concrete attains its full strength, the cables or wire is stretched to this jig and also anchored on this side. This is anchored already on this side. So through this end anchorages, the stress will be transferred to concrete beam. However, it is possible to inject grout from the side of the beam or along the length of the beam, so that this unbonded tendon is it becomes bonded tendon after the injection is completed. Okay, several profiles can be chosen in this manner. These are the anchorage devices. You can see this is a conduit which has been placed. This is a post tensioning under progress. You can see some nominal steel wires, steel reinforcing steel, as well as some shear stirrups, open stirrups. This is anchorage plate or block, and these are called wedges. ये wedges इसकी शेप इस तरह होती है कि जब इसमें से आप एक साइड से वायर खींचते हैं, जब उसको छोड़ते हैं तो ये इधर आके इसमें फंस जाता है. इट इज लॉक्ड इन दिस होल. तो इधर लॉकिंग के बाद जो है ये स्ट्रेस ट्रांसफर करता है. और ये साइट के लिए ज्यादा सूटेबल इसलिए है कि एट द साइट यू कैन यूज दिस मेथड एंड द सेम जैक कैन बी यूज्ड फॉर multiple times the same jig can be used for post tensioning. Next, I will show you a video of pre-stressing concrete plant.
This video will explain the entire process of producing a pre-stressed concrete unit at a pre-stressing plant. In this case, a double T. A double T is used primarily in parking structures, but can be used in virtually any type of building, including office buildings, industrial buildings, and schools, to name a few.
Double Ts are kind of a unique product with having a capability of having a very long span. When you start talking long spans, you're talking 60 feet plus, and sometimes goes as high as 120 feet.
The typical day of a pre-stressing plant usually starts very early in the morning. The product from the previous day's casting has cured by now, and the pieces need to be stripped from the form to get ready for today's casting. For any pre-stressing plant, it is very important to maintain a clean plant. Maintaining neatness is not only positive from an image standpoint, but also from a safety standpoint, since any debris that might be left over from the day before could create a tripping hazard or other safety problem. The first part of the process is setting up of the form. A thorough cleaning of the entire form is done with basic labor and appropriate cleaning equipment. Setting the side forms, or in the case of a typical double T, the forms may be fixed forms with an appropriate draft to allow for easy stripping. Once the bed is cleaned, it's ready for setting up today's cast. This particular bed is set up for 5 double Ts, each about 60 feet long. The bed has a total length of 400 feet. This is a self-stressing form, where the form itself is designed to take the total pre-stress force and compression, and also to handle the eccentricity of the strands. Sometimes the producer may use a form that is set between bulkheads that are built right into the ground. The pre-stressing force is then resisted entirely by the bulkheads and their foundations. Next, the strands are placed in the form and extended from end to end. Crew members thread the strands through each of the dividers and then run them through the stressing plates at each end. The typical spacing of the strands is approximately 2 inches. This divider is a steel device that separates the individual double T units from one another. A gap of about a foot is typical between the ends of the adjacent pieces. This gap is required so the strands can be accessed and cut, and that each double T can be stripped from the forms. The next step is the tensioning of the strands. In this case, we have a strand pattern with straight strands of 6 strands in each stem, as shown here. The strands are first tensioned to about 2 to 5 kips based on the gauge pressure reading. In this case, a mark is made on the strand after the preload is applied. The strand is then tensioned to the specified level and is measured using the gauge pressure on the hydraulic pump. The QC technician then checks the elongation against the theoretical elongation. The requirement that is the force on the gauge and the elongation must match within 5%. If that tolerance is not achieved, the reason must be established and the strand may have to be detensioned and retensioned. After the strands of this double T are all stressed, the remaining embeds are set in place. These include stem reinforcing, lifting devices that will be used to strip and handle the piece, forms for blockouts in the flange, and forms for blockouts in the stems, flange reinforcing, and flange connectors or vectors along the edges. In this case, one of the double T's in the bed has typical flange connectors applied along one edge and special flat plate connectors applied along the other edge to accommodate connections across an expansion joint. The form is now ready to have concrete poured, but only after a pre-pour quality control check has been made and the QC person signs off on it. This QC check can also be done by the bed superintendent and depends on the particular plant's practices. Either way, the check is critical to ensure an end product with the highest quality.
There's all these things you look for, the mesh, you look for anything that could be touching the stems on the bottom, like wire ties that might have fell in there because that would develop some type of little rust spot. You check the length, you want to make sure that the damps are correct. Do we have the strand stripped properly? So there are a lot of critical areas that you need to verify.
Concrete is mixed at the batch plant under tightly controlled conditions. The cement is supplied using tanker trucks. Here, the cement is being blown from the tanker through piping to the cement silos. When needed, aggregates are delivered to bins in the batch plant. The aggregates are stored outside of the batch plant in separate bins. In this case, an enclosed vertical bin system is utilized. During winter, in northern climates, the aggregates must be heated to get them to flow properly through the batching system and to maintain proper concrete mix temperatures. Payloaders are used to shuffle the materials to the conveyor belt. Computers are used to proportion the materials for the desired concrete mix. Cement, sand, stone, water, and admixtures are measured according to signals from the computer. After the concrete is mixed, it is discharged into a delivery device. It's imperative that the concrete mix be delivered to the form as soon as possible. These vehicles are called tuckers, and they are used to deliver the concrete to the bed in the yard. A self-consolidating concrete is being used to cast these particular double T's. With this type of concrete, vibration is not required to consolidate the concrete. However, minor controlled vibration is used in the double T stems to help remove air from the sides of the form, reducing bug holes in the stems. There are many advantages in using this type of concrete.
We do use self-consolidating concrete for our double T's. We feel that it gives us a better finish. We feel that it's easier to place, takes less labor, less strain on labor to place that concrete.
The QC department will make the necessary tests at this time, including a temperature check of the concrete. Since SCC is being used here, a spread test is done to check the concrete flow in lieu of a slump test. The spread is measured to assure conformance to the planned spread. The edges of the circle of concrete are also inspected to check for segregation. The appearance is translated to a visual stability index number. There is a check for air content. Cylinders are filled and will be used later for strength tests of the cured concrete. Back at the bed, the concrete placement continues. A vibrating screed is used to level the surface evenly. A bull float is also being applied to the surface to minimize the potential for plastic shrinkage cracking. The final finish will vary depending on the use of the double T. If a cast-in-place topping is necessary, the surface will be made very rough so that a good bond will be achieved. If it is a roof, the finish will be relatively smooth, but not necessarily perfect. In this case, the surface is broomed as these double Ts are being used in a parking structure. Different patterns can be applied depending on the needs of the project. The bed is now in its curing stage. Sometimes, particularly in cold climates, the double T may be covered with tarps. In other areas, they may be open. Accelerated curing is often done using live steam or radiant heat from heaters attached to the form itself.
Double Ts for parking garages really need to be held to a high standard. When they're assembled in a garage, they make the finished surface. There are tolerances for putting these pieces together, offsets in the surfaces. All of the connections are very sensitive as well to be executed properly. The embedments in the double T have to be placed properly. So there, again, are a lot of critical issues that you have to be concerned with to get proper performance out of that simple double T.
After 12 to 16 hours of curing, the Ts are ready to be stripped. The QC department first tests the concrete to be sure it has achieved the strength required to detension the strands, typically 3,500 psi. This is a typical test being conducted. The strands are detensioned in a specific sequence established by the QC department or the plant engineer. Here, personnel are positioned at each end of the bed and at some of the intermediate bulkhead locations. On a signal, they burn the strand at each end. After all the strands are cut and block-out formwork has been removed, the Ts are stripped from the form. Cables are attached to the lifting devices, and each piece is removed and transported to a detailing area for any minor cosmetic touch-ups. Also at this time, the QC department does a post-pour QC check on each piece that is brought to the detailing area.
When I first get back there, I go and check the length of the piece, verify that within, there's a tolerance of probably a quarter inch or so. Check the width, we check the vectors, we check the electrical blockouts. I do a visual for any type of discoloration in the stems underneath the piece, any type of surface cracks, bug holes, just do a complete visual.
Any defects are noted so that repairs can be done before shipping the T. After all the work is completed, the double Ts are moved into the storage area where they are typically stacked using appropriate dunnage located near the ends. When the job site requires the T to be shipped, it is loaded on a trailer and transported to the job site. What you have just observed is the process for making one type of pre-stressed product. These other types are made using essentially the same process. Hollow core plank, which are used for floor and roof components in multifamily housing, schools, hotels, and many other buildings. Inverted T-beams, which can be used in any total precast concrete build system. Columns, which are cast horizontally and then rotated in the air at the job site. They are often designed as pre-stressed components. Architectural spandrels used in office buildings and parking structures can be made using the pre-stressing process. Deck slabs and box beams, which are used primarily in short span bridge construction. Standard AASHTO girders, which are used in long span bridge construction. Standard bulb tees are also used in long span bridge construction. Pre-stressed piles that support any type of building in areas that have unfavorable soil conditions. As you can see, there are many types of pre-stressed products available. The variety of products that can be pre-stressed in a long line operation is almost unlimited and is up to the imagination of the design professional.
We really do encourage our customers and architects and engineers to get to our plants to really understand how precast concrete is made. They need an understanding of the high quality that they can get out of precast concrete as opposed to
cost effectively as we can, but also as well as we can. And it's not only my responsibility, but the responsibility of everybody here, management, labor, everybody included, to do the best job that they can to, at the end of the day, make a little bit of money, but also have a customer that's very happy and will possibly want to have some return work coming back our way.
Please stress concrete video and get. Please stress post tension. I will show you another video of post tensioning now. Okay, post tensioning. Okay, so this is the end of the lecture. You have seen 2 videos, one on pre-tensioning and another on post-tensioning. Both the videos will be uploaded also in the Google Classroom if you want to watch the videos later. If you have any question about the pre-stress concrete, you can ask your question, please.
Excuse me, sir.
Any question?
सर ये फाइल हम इस मेथड से प्रीकास्ट और स्ट्रेस से तैयार कर सकते हैं?
क्या चीज?
फाइल्स सर ये
हाँ,
जो
बिल्कुल तैयार
हम
कर सकते हैं, बिल्कुल कर सकते हैं। उसको फिर ड्राइव करते हैं थ्रू हैमरिंग, यानी उसको मशीन के जरिए से ड्राइविंग करते हैं ना उसको। उसके लिए एक उसका जो एंड पे डिवाइस होता है ना, उसको लगाकर उसको ड्राइव करते हैं। जिस तरह के आप जानवर को बांधने के लिए हम वो लगाते हैं ना जमीन में पिग, तो उस तरह से उसको ड्राइविंग करते हैं। और वो आर ड्रिवन पायर्स, दे आर कॉल्ड ड्रिवन पायर्स एंड प्रीकास्ट ड्रिवन पायर्स। ठीक है, एनीथिंग एल्स
सर?
जी प्लीज।
सर ये पोस्ट टेंशनिंग में तो हमारे पास ये हाई स्ट्रेंथ स्टील की जरूरत नहीं होगी ना सर, क्योंकि उसमें तो वो क्रीप और स्ट्रेंथ तो पहले से हो जाता है, तो उसमें वो स्ट्रेस ज़्यादा नहीं होगा सर।
किस तरह, दोबारा बताएं
सर? पोस्ट टेंशनिंग में सर हाई स्ट्रेंथ और स्टील की जरूरत तो नहीं होगी ना सर, उसमें 40 KSI भी तो यूज कर सकते हैं।
क्यों नहीं होगी?
क्योंकि सर पोस्ट टेंशनिंग में तो हमारे पास वो कंक्रीट में जो क्रीप और स्ट्रिंकेज हो जाता है वो तो पहले से हो जाता है सर, जो बाकी बच जाते हैं 40 KSI सारा स्ट्रेस।
व्हाट इज क्रीप जरा आप डिफाइन करें। क्रीप क्या चीज है? क्रीप जरा डिफाइन करें। क्रीप जब आप फोर्स लगाएंगे उसके बाद क्रीप आएगा ना। क्रीप तो वैसे नहीं आएगा ना। क्रीप तो कांस्टेंट फोर्स पे आएगा। जब फोर्स आप लगा देंगे तो उसके बाद क्रीप आना शुरू। श्रिंकेज तो आ जाएगा, श्रिंकेज पहले से हो चुका होगा। लेकिन श्रिंकेज और क्रीप जो है ये टाइम डिपेंडेंट फिनोमेनाज है ना। टाइम के साथ आहिस्ता आहिस्ता ये क्रीप और श्रिंकेज कंक्रीट के सेक्शन को रिड्यूस करेंगे। तो स्टील में जो पहले से स्ट्रेचिंग आपने की थी वो उसको स्टील जो है वो लॉस करना शुरू कर देगा। इसकी वजह से उसमें प्री स्ट्रेस लॉस आ जाएगा। ठीक है, ये तो हमने सिर्फ 2 चीज़ों की बात किया। अगर अदरवाइज इलास्टिक शार्टनिंग भी है, रिलैक्सेशन भी है, तो इन सब चीज़ों की वजह से हाई स्ट्रेंथ स्टील के बगैर आप इसको नहीं कर सकते।
ओके सर।
एनी अदर क्वेश्चन?
सर ये जो आई शेप वो जो गर्डर आपने बताया था प्री टेंशनिंग वाले पोर्शन में,
हाँ
सर तो उसमें आपने कहा था कि ये जो स्ट्रेचिंग वाइज जो स्ट्रेच करते हैं जिस
हेलो, आवाज आपकी कट गई है दरमियान में, मैं नहीं सुन सका। बदल जाना माजूर आवाज की बात जी। कनेक्शन लॉस्ट कसूश। हेलो, आप क्वेश्चन दोबारा करें, आपका क्वेश्चन हम नहीं सुन सके। आप कौन बोल रहे हैं? हेलो हेलो, आप मुझे सुन रहे हैं इस वक्त? आप लोग, मेरी आवाज आ रही है आपको?
जी
अच्छा, वो क्वेश्चन मैं नहीं सुन सका, किसने क्वेश्चन किया था, लेकिन मैं सुन नहीं सका। फयाज
सर वो लीव डिस्कनेक्ट हो गए सर।
अच्छा, रुक सकते हो? क्या क्वेश्चन था, आप लोग सुन सके उसको?
नो सर।
एनी अदर क्वेश्चन? किसी का और कोई क्वेश्चन है?
नो क्वेश्चन सर।
Okay, we will wait for a couple of minutes if there is any question. Otherwise, the lecture is over. You can go through the lecture once again, and if you have any question, you can come up with your question in the next week lecture.
Thank you, sir. Assalamu alaikum, sir.